It's the weekend, so perfect time to chat about plasma, right? Hello, my name is Greg Friedman. I'm a PhD bioengineer and I work in electric discharges. I study them, I control them, and on this channel I talk about them. So in today's episode, let's talk about, can plasma be scaled up? That's a question that comes up very often in multiple discussions. And I wrote down 14 points for this discussion. So this might end up being a longer video. So you made something in the lab. It works. Under lab conditions, everything is perfectly controlled. You're using ultra pure water, your power supply is stable, and you got the result. Now it's time to commercialize it. Scale it up, make it bigger. Well, first issue is, when you make plasma bigger, is it going to stay the same? How are you going to keep the same plasma regime? Maybe you took some bacteria on a petri dish and you used micro plasma jet, millimeter or two in diameter, to kill the bacteria. Well, how are you going to scale that up to treat a whole entire strawberry? Matter of fact, you need to do that in a fraction of a second at a very, very small fraction of a penny. So just because it works in a lab doesn't mean it's going to work the same when it's bigger. Is your jet, if you make your jet from 2 millimeters to 10 millimeters to 5 inches, is it going to be the same jet? Next issue is power supply scaling. So your power supply can easily supply a couple of watt that the tiny plasma needs. What about a kilowatt or 100 kilowatt? What's that power supply going to look like? And how much is it going to cost? Is it even feasible to make transformers that size? Or maybe you want to increase distance between electrodes. That creates lots of challenges because when you increase distance, you increase voltage. At 10,000 volts, you have steady plasma, no issues. But when you approach 100,000 volts, you have a very interesting phenomena called Bremsstrahlung radiation. It's basically electrons smashing into the surface at very high energy, decelerate and cause emission of hard X-rays. So above 100,000 volts, you start seeing hard X-rays emitting from your machine. How's your occupational safety and health guys going to look at that? That's an issue. Next one is uniformity of your treatment. So let's say if you make a small dielectric barrier discharge, it's comparably easy to keep it uniform. But when you want to treat, 8-meter wide print using your dielectric barrier discharge, you need to keep those electrodes insanely, perfectly parallel everywhere throughout the entire 8-meter width. So uniformity is a big issue, because if you have a slight non-uniformity somewhere in that whole big line, well, that's where plasma is going to not happen if the distance is a little bigger, or that's where the plasma is going to concentrate if the distance is a little smaller. And when I say little, in case of dielectric barrier, even 100 micron, a few thousandth of an inch, matter. Next one, gas flow and mixing. They don't scale up that simple either. So you have, especially if you're using specialty gas or gas with some kind of a reactant, when it's really, really tiny on a lab scale, mixing often isn't an issue. You just plasma treat that volume of gas, have it react, and then you have your reactants. But what if you go from a cubic millimeter of gas to cubic feet, to cubic meters, to tens of cubic meters? Gas flow and mixing, gas dynamics, especially gas dynamics in something like non-equilibrium plasma. It's called non-equilibrium for a reason. It's not in local equilibrium. So gas flow and gas mixing, big issue. Next one is heat management. Again, when you're talking lab scale, look, plasma, there's no magic. When you generate plasma, there is some heat that is released. Even in so-called cold discharges, there is some element of temperature. And eventually, everything relaxes to temperature. So eventually, you will see temperature increase. On a lab scale, that increase may be so tiny that you can't even notice. But on a large scale, you need to start thinking about managing heat. In other issues, when you're talking about industrial scale, those systems have to work unattended for hours, days, maybe months, or even years. Water treatment facilities, they work frequently 24/7 for years without replacing parts, without fail. Because if you do fail, you stop drinking water for an entire region. Not good. So electrode, erosion, and durability of your setup, they become increasingly important, including cost. I frequently use quartz for my dielectric, fused silica. Why? Because it's very clean material, it's very nice to work with, and it's comparably inexpensive when you talk about small-scale lab stuff. When you start talking about big quartz plates that are perfectly parallel, the price goes up quite a bit. So you can switch to cheaper dielectric material or even plastic. But how durable is it? Is it going to break in a day or two, stopping the entire process, and it's going to be your fault? So scaling needs to consider electrode erosion and durability. Next one is chemistry. Chemistry changes with scale. Again, it's all these non-uniformities. Take ozone production, for example. Ozone is produced in oxygen-containing plasmas. But plasma is good at producing ozone. Plasma is also good at destroying ozone. So problem with industrial ozone generators, big machines. You need to design the machine very cleverly so you maximize ozone production and you minimize ozone destruction, which isn't something you readily see on a very tiny lab scale setup. You also have mass transfer limits. If you're using plasma to generate some kind of a material, well, how are you going to transport it out of plasma? Same problem as with ozone. Lab scale, well, with ozone production, ozone is what you're producing. So there is your mass transfer limit. You also might want to check on the plasma, see if it's working correctly. Lab scale, easy. Look at it, put an optical emission spectrometer, diagnostics. Looking at it, listening to it, looking at it with an optical emission spectrometer, all of those are diagnostics and they're readily available, in a nice, well-lit lab environment. They're not so readily available when your system is huge. You can't put 500 optical emission spectrometers. The price becomes ridiculous. So diagnostics becomes harder with scale up. Energy efficiency. Maybe you got, on a lab scale, you got your energy efficiency 95%. Is it going to scale up when you go to bigger systems? So energy efficiency is something that needs to be considered during scale up too. For all these reasons, when you talk about scaling up plasmas, you usually consider, instead of monolithic scale up, like making your electrode 100 times bigger, making your power supply 100 times bigger, maybe making everything 100 times bigger just to get 100x the product, maybe you want to go modular. Even I saw multi-100 kilowatt industrial ozone generation systems that are huge, few meters by few meters by few meters, big systems generating lots of ozone. But if you open, you see hundreds of smaller electrodes. So modular is probably the way to go for many of the plasma scale-up processes. Another thing to consider as you scale up, your safety and your regulatory issues follow, right? So let's say you have to, for your scale up, you have to go, as I mentioned, to more than 100 kilovolt, more than 100,000 volts. Well, now you have X-rays. So safety issues are very important to consider during scale up, as well as regulatory issues. How are the regulatory authorities, Center for Disease Control, Food and Drug Administration, United States Department of Agriculture, etc., how are they going to look at your system? Lab scale is one question. And probably you're working at university. There are a lot of regulatory, how do I say, easements for the university. It's a lot easier to do a lot of the work, but when you go to scale, if your process produces ozone and you're dumping it out into the environment, well, how much of it and what are the regulatory bodies going to think about that? Can you manufacture at scale? Again, back to hundreds, thousands of electrodes used in ozone generation. How manufacturable are those and how repeatable is the manufacturing process? What errors, what uncertainties, and what percent differences between the electrodes? All of those become issues. And finally, control and feedback. How does a larger system talk to other equipment in the facility? How do electrodes talk between each other? I mentioned most of this, but diagnostics and power supplies, plasma power supplies, high voltage, there's a lot of emission in the electromagnetic spectrum. How are you protecting one power supply from interfering with the other power supply and from all of them interfering with other equipment in the facility? Lots of issues. So when you talk about plasma scale-up, there are lots of things you have to consider. I'm sure it is similar in other technologies. Lasers are notoriously hard to scale up. I would imagine metallurgical processes, it's not so easy to go from in the lab to an industrial manufacturing process. That's why it costs so much frequently. But anyway, I hope the simple question of can plasma scale is somewhat answered for you now. My intent was to raise more questions than give answers. I just wanted to chat about complexity of stuff that us plasma engineers have to deal with, and it's pretty cool. The field is wide open. We need more people. So if you're interested in this field, go to school, study plasmas, and come help us scale them up. Peace. I'll see you in the next one.